Hello, this is Dr. Michael Olson with Meteorology 2010. We're in the middle of discussing Chapter 2 from our meteorology textbook, Essentials of Meteorology. We are talking about warming the atmosphere and how the Earth retains its heat throughout the day and even through the night as well. We've already talked about definition of energy and heat, and this video will commence talking about the second topic, the energy budget. What we mean by the energy budget is a balance between incoming radiation and outgoing radiation, and just balancing all the incoming and outgoing energy so that we maintain a stable temperature. So we start off with the question, if the Earth is always radiating energy away, why isn't it always cold? And if the Earth is always radiating energy away, we are losing our energy, our temperature should drop. The answer is the energy budget, or the balance of heat in the atmosphere. So we need to talk about something called radiative equilibrium, which is exactly that, the balance between incoming radiation and outgoing radiation. Let's take the example here on the left. Let's say we have a snowy surface. You have energy coming in from the sun. It hits the snow, but snow is quite reflective, and so it just reflects and goes back out to the surface. As a result, the Earth will not absorb as much energy, but it will still emit infrared energy away since it has a temperature greater than absolute zero. So in this case, we're going to be emitting more energy than we can absorb, since the incoming solar energy is just reflected away. Since we're emitting more radiation than we are absorbing, we are going to have a net loss of energy, and thus the temperature will be colder. Now, on the other hand, let's take this figure on the right, where instead of a snow-packed landscape, it's now clear of snow, green, and we have grass, which is very good at absorbing solar radiation. As the solar energy comes in, we absorb a lot more radiation, and we emit energy as well. And then here, we're also including a balance from the atmosphere itself, which comes into play as well, and we'll discuss that in a little bit. But since in this case we are absorbing more than we are emitting, there's going to be a net gain of energy. And since we have a net gain of energy, the temperature is going to increase and we will end up with a warmer environment. Okay, one of the things that helps most with this, as we actually saw here in this figure, I apologize for going back, one of the things that helps most in this balance of energy is greenhouse gases. So let's talk now about greenhouse gases, what they are, and how they help with the atmosphere. So there are some elements in the atmosphere that are very good at absorbing infrared radiation from the Earth's surface. But these elements in the atmosphere may be good at absorbing certain wavelengths, but not other wavelengths. These gases are known as greenhouse gases. The most common greenhouse gases we deal with are gases that absorb Earth's infrared radiation, but they allow visible light to pass through. This allows sunlight to reach Earth's surface, since it's not absorbed by the Earth's atmosphere. But then when the Earth radiates energy away, it's often trapped by these greenhouse gases, thus keeping the Earth warmer. And important to note about these gases is that if it's good at absorbing energy, then it's also good at emitting energy. Okay, here is a figure showing a handful of gases in the atmosphere and at what particular wavelengths they are good at absorbing radiation. So if we look here, we have nitrous oxide and methane. They're not very good at absorbing most wavelengths, but there are 2 peaks for each gas. But they are exceptionally good at absorbing radiation. Here's another good one, oxygen and ozone. Oxygen is very good at absorbing certain wavelengths of infrared radiation. But over here on the left side, we have very short wavelengths. These short wavelengths are in the ultraviolet spectrum. Now, let me see if I can zoom in here a little bit. If I can, here we go. I can do this. O3 makes up ozone. Okay? So, ozone is very, very good at absorbing ultraviolet radiation. Now, if you remember back from chapter 1, part of the makeup of the stratosphere is the ozone layer, a layer of ozone inside the atmosphere, which increases in temperature because it is absorbing precisely this, ultraviolet radiation. That's why the stratosphere is so much warmer than the troposphere. So there's that as well. Water vapor is very good at quite a few wavelengths, especially the really long wavelengths. Carbon dioxide also here. When you add it all together, you get a spectrum that looks like this bottom figure. Notice there are 2 gaps. One here, where the gases in the atmosphere do not absorb visible sunlight, so it allows visible sunlight to pass through. And there's also a pretty large gap, with the exception of one spike in the middle, in the infrared spectrum. That allows some of the Earth's infrared energy to radiate outwards. You can think of it as a safety valve. It keeps the Earth from getting too hot. Having an idea now of these greenhouse gases, we're ready to talk about something called feedback. Feedback is basically when you have some sort of a cause. The feedback is what the effect of that cause will do to the initial cause itself. There are 2 types of feedback. There's a positive feedback, where some effect enhances the initial cause. So for an example, let's increase carbon dioxide. If we increase carbon dioxide, then the amount of infrared radiation that it absorbs increases. And if it absorbs more radiation, then it's going to increase the temperature. And if it increases the temperature, that's going to release more carbon dioxide into the atmosphere. You've got yourself a loop. So increase carbon dioxide, you increase the temperature, which increases the carbon dioxide, which increases the temperature more, back and forth. It just progresses and enhances itself. Now, the opposite of a positive feedback would be a negative feedback, where the effect counters the initial cause. For instance, if you increase the temperature, you're going to increase the amount of water vapor in the air, which will increase the number of clouds. Well, if you have more clouds, that's going to reflect more sunlight back out into space, which is going to result in a net loss of energy or a decrease in temperature. So both of these feedback mechanisms play a huge role in balancing the amount of energy the Earth absorbs and releases. In other words, it's an important part of the energy budget. Okay, so let's take a closer look at this the total spectrum of radiation that is absorbed by our atmosphere. I already made this point. Dry air is not very good at all at absorbing visible wavelengths of radiation, so it passes through the atmosphere, reaches the ground without warming the atmosphere at all. So sunlight will come, hit the surface of the Earth, and warm the surface directly. And after it warms the surface, Then you've got yourself hot patches of the surface on the ground. And through conduction, it will start to warm up the air directly above, in which case you have convection that will start to happen. You develop convection cycles, and latent heat is released as that water vapor cools and condenses in the form of clouds. And there you have conduction, convection, and radiation, both incoming and outgoing by the Earth, all playing a role together to create a good balance of the energy throughout the atmosphere. All right, so now we can talk a little bit more about shortwave radiation, or visible light. Now there's a term that's tossed around in the book a fair amount. It's called insolation. That's short for incoming solar radiation that reaches the atmosphere and the Earth's surface. So we'll focus more on this insolation in a little bit. An important term to know now, but we're going to focus on two other points here to finish up this video. The first is if the radiation doesn't reach the atmosphere or the Earth's surface, that means it's being reflected back outwards. That rate of sunlight reflection is what we call albedo, the rate of reflection of insolation. Now, the different materials will reflect at different rates. For instance, a layer of fresh snow will reflect 75 to 95% of sunlight, whereas grassy, dry ground will reflect only 5 to 20%, or maybe 10 to 30%, depending on soil cover. And you can see all sorts of other albedos here. This figure's in your book. You can look at that a little bit more. Now, here's a really fun point talking about scattering. When sunlight comes into the atmosphere, it's going to hit molecules in the atmosphere, and as it hits those molecules, the sunlight's going to scatter in different directions depending on the wavelength. Generally, the longer wavelengths, in other words, red light and orange light, will scatter forwards, whereas the shorter wavelengths, blue light, green light, and violet, are scattered more sideways. So now we're ready to answer a really great question: why is the sky blue? Common myth is that it's blue because it's a reflection of the ocean. Other way around, the ocean is blue because it's a reflection of the sky. Here's why the sky is blue. As sunlight passes through the atmosphere, it passes through and it scatters. Now remember that as it hits these molecules, the reds and the oranges and the yellows scatter forwards. That's why when we look at the sun, it looks more of an orangish, yellowish color, because those are the wavelengths we're seeing from our atmosphere. But as it passes through hits other molecules, the blue light and violet light are scattered more sideways. And so, standing here on the surface of the Earth, from the sunlight hitting other portions of the atmosphere, it's the blue light that is scattered towards us. So, most of the atmosphere, we see blue light scattered sideways coming towards us. That's why the sky looks blue. But when we look directly at the sun, it looks reddish, orangish, or yellowish. Especially around sunrise or sunset, where the sunlight has to pass through more of the atmosphere, more of the blues and reds are filtered out, even some of the yellows, and so you end up with a very orangish, reddish sunset. All right, so this concludes most of the discussion on the energy budget, all the preliminary stuff. We are now ready to talk about the energy budget itself, which will be discussed in the next video.